Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
It really is a pleasure to be back.
This is Andrew and Renee. Welcome to the Stack series.
Always a great time exploring the stacks with you.
Today we are exploring the philosophy of physics, the intersection where hard science meets the deepest questions of reality. And honestly, I have to confess something right off the bat. When I saw the stack of research for this exploration, I felt a little bit of panic.
Panic? Why is that? I mean, it's just physics.
Just physics, right? Well, usually when we cover a topic, I feel like I have a decent handle on the basics, you know? But this is incredibly intimidating. We're talking about the fundamental nature of reality itself. We tend to think of physics as the domain of the concrete labs, lasers, particle colliders, chalkboards full of undeniable math.
Yeah, the hard, tangible stuff.
Exactly. And then we think of philosophy as, well, people in tweed jackets smoking pipes in armchairs asking things like, but what is a table, really?
That is the classic stereotype, isn't it? The doers versus the thinkers. The lab coats versus the armchairs.
Right. But the aha moment for me, reading through these sources, was realizing that this distinction, this massive wall we've built between physics and philosophy, is actually a really new invention. For the vast majority of human history, those two jobs were the exact same thing.
Precisely. And that is exactly where we have to start our discussion today. Because if you could somehow hop in a time machine and go back to the 17th century, and you walked up to Isaac Newton and said, "Sir Isaac, you are the greatest scientist who ever lived," he would have looked at you like you were speaking complete gibberish.
Because the word scientist just didn't exist yet.
No, it didn't exist at all. He would have had any clue what you meant.
Yeah.
Newton called himself a natural philosopher. His most famous book, the Principia, the book that basically invented modern physics, is actually titled Mathematical Principles of Natural Philosophy. Yeah. He wasn't just trying to figure out the math of how apples fall or how planets orbit. He was trying to figure out the philosophical nature of the reality in which those apples exist in the first place.
So if Newton was a philosopher, when did we decide to file for divorce? When did physics sort of pack its bags and move out of the philosophy house?
It's surprisingly recent, actually. It happened in 1833.
1833. That is remarkably specific.
It is, yeah. There was a meeting of the British Association for the Advancement of Science. A man named William Whewell stood up. Now, he was a philosopher, a historian, and a theologian. He looked around the room at these men who were studying geology, chemistry, and astronomy, and he realized the old term natural philosopher, it just didn't quite fit what they were doing anymore, so he coined the term scientist.
And that's the moment the split happened, just like that.
That was the catalyst, yes. Whewell wanted to distinguish those who were digging into the material world, the how, from those digging into the metaphysical world, the why.
And reading through the sources, it really seems like that split came with a massive cost. One of the papers described it as an ontological vacuum.
Yes. Ontology, for those listening who might not use that word every day, is the philosophical study of being. It's the study of existence itself. When science split from philosophy, it became incredibly efficient at quantitative modeling. We got very, very good at predicting what happens.
Right. The math.
Exactly. We have equations today that can land a rover on Mars with pinpoint accuracy. But in doing so, we sort of stopped asking why it must be that way. We have the math, but we lost the metaphysics to explain what the math is actually describing underneath it all.
So our mission today with this stack of research is to try and fill that vacuum.
In a way, yes. Our mission is to unpack the fact that modern physics, things like relativity, quantum mechanics, thermodynamics, hasn't actually solved the philosophical problems of the past. In fact, our sources heavily suggest it has just created new, much weirder ones.
Yeah.
We aren't just talking about how the universe works today, we're asking what it actually is.
Okay, let's unpack this step by step. We're going to structure this discussion by starting with the foundations, what we think we know. Then we'll move to the active debates, where the science totally disagrees, then the frontiers, where things get really strange, and finally, the implications for us regular people going about our daily lives.
So like a solid plan?
So foundations. We have to talk about Newton, because we have this image of him as the ultimate rationalist, right? The cold, hard logic guy. I don't guess, I calculate.
He certainly wanted people to think that about him. He had a very famous catchphrase in Latin, hypotheses non fingo. It translates to, I feign no hypotheses. He claimed he didn't speculate. He just looked at the data and wrote the law.
But based on the research, that wasn't true at all, was it?
Not even close. If you actually look closely at his work, His entire theory of gravity relied on massive philosophical leaps that genuinely terrified his contemporaries. Think about gravity for a second. Really think about it. Newton said that the sun pulls on the Earth instantly across millions of miles of completely empty nothingness.
Action at a distance.
Exactly. To a mechanical philosopher of his time, someone like Descartes, that sounded like literal magic or the occult. How can a thing push or pull something it isn't touching? If I want to move this coffee mug on the desk here, I have to touch it. I want to move a car, I have to physically push it. But the sun just grabs the Earth through the void.
When you put it that way, it does sound like telekinesis. It sounds absurd.
It was a huge problem for him.
Yeah.
To make that math work, Newton had to invent a philosophical concept called absolute space.
Okay, this is the first big concept we really need to nail down for you listening. Absolute space. To me, space is just emptiness. It's where the stuff isn't. It's just the gap between things in the room.
That's the common intuition, sure. But Newton needed space to be a thing. Imagine a container. An invisible, infinite box with rigid grid lines. Even if you took every star, every planet, every single atom out of the universe, if you just deleted all the matter entirely, Newton believed that the box of space would still be there. It is a container that exists completely independently of the stuff inside it.
So space is a stage, and the planets and stars are just actors. If the actors walk off, the wooden stage is still sitting there in the dark.
Perfect analogy. This view in philosophy is called substantivalism. Space is a substance. It has its own reality.
But not everyone agreed with him on this stage idea. Enter the villain of the story, or maybe the hero, depending on your perspective, Gottfried Wilhelm Leibniz.
Leibniz was Newton's great rival. They famously fought over who invented calculus, which was a very nasty public feud, but they also fought bitterly over the fundamental nature of reality. Leibniz argued for something called relationism.
Relationism. Okay, help me out here. How is that different from Newton's infinite container?
Leibniz said space isn't a thing at all. Space is just the relationship between objects. If I am 3 feet away from you right now, that 3 feet is a spatial relation. But if you take me away, and you take yourself away, and you take the microphones of the desk away, the space ceases to exist. There is no stage. There are only the actors and where they stand relative to each other.
That breaks my brain a little bit. If there's nothing there, how can there be distance?
That was exactly Leibniz's point. Distance is a property of things, not a property of the nothingness between them. He had a very clever philosophical argument against Newton here. He said, imagine God creating the universe. If Newton is right, and there was this giant, infinite, uniform container called absolute space, God has to decide exactly where to put the universe inside it.
Okay, I'm tracking with that.
But if space is perfectly uniform, if every single spot in the infinite void is completely identical to every other spot, why would God put the universe here and not, say, 5 miles to the left?
There would be no reason. It would be exactly the same.
Exactly. It would be a completely arbitrary choice. And Leibniz firmly believed God didn't make arbitrary choices. Everything had to have what he called a sufficient reason. Therefore, since there is no reason to pick one spot over another, absolute space must not exist. The position of the universe is only defined by the things inside the universe.
So we have the container, which is Newton, versus the web of relations, which is Leibniz. This was the first great debate in our sources. Who won?
Well, physics sided with Newton for a very long time simply because the math worked so well. Newton's laws were incredibly successful at predicting planetary motion, eclipses, everything. But philosophically, it was a mess. It took Immanuel Kant to try and rescue the whole situation.
Kant, the absolute heavy hitter of philosophy. I remember struggling through Kant in college and just getting completely lost.
Everyone struggles through Kant, don't worry.
Mm-hmm.
But his solution to this specific problem was undeniably brilliant. He looked at this debate and realized that Newton's physics worked perfectly, but it completely lacked metaphysical grounding. So Kant came up with transcendental idealism.
Talk about a mouthful.
It's actually simpler than it sounds once you break it down. Kant said, what if space and time aren't things out there in the physical world at all? What if they are just software running in our heads?
Whoa, wait, so space isn't real, it's just a hallucination.
Not a hallucination. Think of it more like a VR headset. Imagine every human being is born with a permanent, irremovable VR headset glued to their face. This headset has built-in software that organizes all the raw data coming into your senses. The software automatically organizes things into left and right, up and down, before and after.
So he literally can't see the raw world without the headset formatting it first.
Exactly. Kant argued that space and time are forms of intuition. We cannot experience the world except through the lens of space and time. They are the framework our mind rigidly imposes on reality to make sense of it, not objects floating around in the void.
So if I ask Kant, does absolute space exist, what would he say?
Kant would say, for us, it absolutely must. We have to organize our human experience that way. But we can't possibly know if it exists as a thing in itself outside of our own perception. He basically saved Newton by moving space from the outside physical world into the internal human mind.
That is surprisingly convenient. It basically says, hey, Newton is right about how we see the world, so keep using his math, but we don't have to prove the universe is actually built like a box.
It was a brilliant, elegant compromise. And for a long time, that seemed to settle things down. But then, as we move into the second section of our discussion, the active debate science didn't stay with Newton forever. We got Einstein.
And this is where things start getting really messy in the sources. Because Einstein didn't just tweak Newton's ideas, he completely overhauled them.
He did. And this brings us right back to the fundamental nature of space, or, as we have to call it now, space-time.
I want to go back to the bucket for a second. I saw in the research notes something called Newton's bucket. It sounds like a bad magic trick, but apparently it's a devastating philosophical argument against Leibniz and relationism.
It is a brilliant thought experiment. Newton used it to prove his absolute space was real, and honestly, it still haunts philosophers today. Imagine a wooden bucket half filled with water, hanging from a long rope. You twist the rope up tight, really tight, and then you let go. The bucket naturally starts to spin as the rope unwinds.
Okay, I'm picturing it. It's just a spinning bucket.
At first, just the bucket is spinning. The water inside is still perfectly flat because the friction from the wood hasn't caught the water yet.
Right, the water is stationary, the wood is moving around it.
Then, slowly, the friction catches, and the water starts to spin along with the bucket. And as it spins faster, what happens to the surface of the water?
It pushes out to the sides, it becomes concave, like a little whirlpool in the bucket.
Correct. Centrifugal force pushes it up the sides. Now, here's the trick. You reach out, grab the bucket, and stop it dead from spinning. But the water keeps spinning inside it for a little while due to momentum.
And the water stays concave while it's spinning.
Yes. Now, Newton asked a devastating question. What is the water spinning relative to?
Well, the bucket.
No. Think about it. In the beginning, the bucket was spinning and the water was flat. The water and bucket were moving relative to each other. At the end, the bucket is stopped and the water is spinning. Again, they're moving relative to each other. The relative motion between the water and the bucket is exactly the same in both cases, but the shape of the water is completely different, flat versus concave.
Oh, I see. So the water isn't reacting to the bucket at all.
Exactly. Newton said, the water is spinning relative to absolute space itself. The water somehow knows it is spinning. It feels the physical force. Even if you did this exact experiment in deep, dark space with no Earth, no stars, no nothing around you, Newton said the water would still curve up the sides. Therefore, space must be a real thing that pushes back on the water.
That seems really hard to argue with. The water physically changes shape. Something invisible has to be causing that change.
It stumped the greatest minds for centuries, until Ernst Mach, the physicist that Mach speed is named after, came along and said, hold on a minute, maybe the water is spinning relative to the distant stars.
The stars. What do the stars millions of light years away have to do with a bucket of water?
Mach argued that inertia, which is the resistance of any physical object to a change in its state of motion, is actually caused by the gravitational pull of all the other matter in the entire universe. He said if the universe were completely empty except for that one bucket, the water actually wouldn't curve. It only curves because it's rotating relative to the gravitational field of the rest of the universe.
So relationism strikes back. It's not the invisible container of space. It's the web of other stuff in space acting on the water.
Exactly. And Einstein absolutely loved this idea. He called it Mach's principle. He really, really wanted to build his theory of general relativity on this exact idea. He wanted to kill Newton's absolute space once and for all.
But he failed. The sources imply that didn't go as planned.
He sort of accidentally made space even more real than Newton did. Because in general relativity, gravity isn't a force pulling things through space like magnetism. Gravity is the literal curvature of space-time itself. Mass tells space how to curve. Space tells mass how to move.
Right. It's the classic analogy of the heavy bowling ball sitting on a trampoline, warping the fabric.
Sure, it works as a basic visual. But think deeply about what that actually means philosophically. If space-time can bend If it can ripple with gravitational waves, if it can expand and wobble, it starts to look a whole lot like a physical substance again. It has measurable properties, it acts on matter. This is what philosophers call substantivalism 2.0.
So Einstein, trying to prove Leibniz right, accidentally proved Newton right. Space is a physical thing.
It really looked that way for a while. But then the philosophers found a massive glitch in Einstein's theory, a paradox that is known as the whole argument.
This was the most technical part of the stack, and I have to admit I read it 3 times and my head was spinning. It sounds like a complex riddle.
It is very tricky, but let's try to visualize it clearly for you listening. Imagine space-time is a physical thing, like a literal piece of stretchy fabric. And on this fabric, you have specific points coordinates, like little metal thumbtacks defining here and there on a map.
Okay, I'm with you. A fabric map with thumbtacks.
If those points, those thumbtacks, are real, distinct physical things, then Einstein's equations run into a huge problem. Because you can mathematically take a completely empty region of space-time, a hole, where there is no matter, and you can shuffle the points around inside it without changing the gravitational field at all.
Like swapping 2 thumbtacks on a corkboard.
Exactly. If the thumbtacks are real, distinct things, then by swapping them, you've created a totally different physical situation in reality. But Einstein's math says the gravitational field looks exactly the same before and after the swap. The math can't tell the difference.
So the math says absolutely nothing changed, but the philosophy says something physically changed.
Which means the theory entirely loses its determinism. You can't predict which specific point will end up where. Einstein struggled with this whole argument for 2 agonizing years. It drove him absolutely crazy.
So we are completely stuck. If space is a real thing, like a fabric, the math breaks. If space isn't a thing, we can't explain gravity and Newton's spinning bucket.
This is exactly where the modern philosophers in our source stack propose what they call a third way. It's known as structural space-time realism.
Structural space-time realism. Okay, decode that for us.
It essentially says, stop thinking of space as a physical container, and stop thinking of it as just empty distances between objects. Think of it as a pure structure. The reality isn't the physical points themselves. The underlying reality is the web of connections.
That still sounds a little vague.
Think of the internet. You can't walk into a server room, point to a specific flashing box and say, this right here is the internet. The internet isn't the copper wires, and it isn't the plastic computers. It is strictly the structure of the connections between them. Structural realism says space-time exists, yes, but it exists as a strict structure of relations of laws, not as a bag of physical points you can swap around.
So the thumbtacks themselves aren't real, but the mathematical pattern they make is the reality.
Precisely. It's a very subtle shift in perspective, but it magically saves the physics. It allows space-time to be real enough to bend and cause gravity, but not so tangible that it creates the whole paradox.
That is heavy. But if we think space is confusing, we really have to talk about time, because honestly, the section on time in these sources gave me a minor existential crisis.
Join the club. The philosophy of time is where physics clashes most violently with our everyday human experience.
It starts with a seemingly simple puzzle, the arrow of time.
Right. In our daily lives, time clearly flows one way, always forward. We clearly remember the past. We anticipate the unknown future. You can easily turn a whole egg into an omelet, but you can't ever turn an omelet back into a whole egg.
But the equations of physics don't care about the egg.
Exactly. If you look closely at Newton's laws, or quantum mechanics, or relativity, the equations are mostly time-symmetric. They work perfectly fine in reverse. If I showed you a video of 2 billiard balls colliding on a table and I played it backward, you literally wouldn't be able to tell which version was reality. The fundamental physics allows both directions equally.
So if the foundational laws of the universe don't have an arrow pointing forward, why do we feel one so strongly? Why does yesterday feel permanently gone and tomorrow feel full of potential?
There are 2 main philosophical camps here. One is called the block universe, which is also known as eternalism.
This is the loaf of bread idea from the reading.
Yes. Imagine the entire history of the universe is a giant, solid, 4-dimensional block, length, width, height, and time. In this massive block, the dinosaurs roaming the Earth are permanently etched down at one end. We are sitting here talking in the middle, and the future human colonies on Mars are already set at the other end. Everything past, present, and future exists completely simultaneously within this block.
Wait, so now this exact moment we are in isn't special at all?
Not in this view, no. Now is just a physical coordinate. It's exactly like saying here, if I say I'm here in New York, that obviously doesn't mean London doesn't exist right now. It just means my consciousness isn't located there. In the block universe, the dinosaurs aren't gone. They're just existing at a different time coordinate that we don't have access to right now.
That makes me feel incredibly claustrophobic. It means the future is already completely written. It's just sitting there, waiting for us to arrive.
Einstein strongly believed this. He explicitly called the passage of time a stubborn illusion. There is a very moving letter in our sources that Einstein wrote to the grieving family of his best friend, Michael Besso, who had just passed away. Einstein wrote, "He has departed from this strange world a little ahead of me. That means nothing. For us believing physicists, the distinction between past, present, and future has only the significance of a stubborn illusion."
Wow, that is beautiful, but also profoundly terrifying.
It completely changes how you view death, doesn't it? In the block universe, you are a four-dimensional worm embedded in this massive space-time crystal. You have a clear start point and a clear end point, and the whole worm just exists eternally.
I really don't like being a worm embedded in a crystal. I like having actual choices. I like waking up thinking that the future hasn't happened yet, and I can change it.
That view would be presentism. The intuitive idea that only the exact now exists. The past is gone, the future's unwritten. But relativity makes presentism very, very hard to defend scientifically
Why is that?
because of time dilation. Your specific now might be totally different from the now of an astronaut moving near the speed of light, because light takes time to travel. What is simultaneous to you isn't simultaneous to someone moving relative to you. If we can't objectively agree on what now is across the universe, how can now be the only thing that actually exists?
Okay, fair point. But if the block is real and everything is frozen, why do we constantly feel time moving forward? Why the strong illusion?
That brings us to entropy, the second law of thermodynamics.
Ah, the coffee cup analogy?
The famous coffee cup. If you pour a splash of milk into black coffee, it naturally mixes. It goes from a state of order, perfectly separated liquids, to a state of disorder, a mixed brown liquid. Entropy, which is basically just a mathematical measure of disorder or randomness, always inherently increases in a closed system. This is the only physical law we have that distinctly separates the past from the future.
So the arrow of time isn't actually about time itself flowing, it's just about stuff getting messier over time.
That's the leading scientific theory. We perceive the future purely as the direction of higher entropy.
But our sources raise a much deeper philosophical question here. Is this arrow intrinsic or extrinsic?
This is where we get into the really deep implications. Is time itself fundamentally flowing, meaning it's intrinsic to reality? Or is it just that the universe happened to start in a very, very low entropy state at the Big Bang, and we're just passively surfing the wave of increasing disorder? That would make it extrinsic.
The sources refer to that as the past hypothesis.
Yes. The past hypothesis is the idea that the flow of time is essentially a statistical accident, because the universe started out impossibly organized and tightly packed. If the universe had somehow started in a state of high entropy, maximum messiness, there might be no arrow of time at all, no flow, no memory, no life.
Wait, back up. No memory. How does the universe's entropy connect to my personal memory?
Think carefully about what a memory is. Forming a memory in your head is a physical process. You are literally arranging physical neurons and synapses in your brain. You're creating a local pocket of high order. But to create that specific order in your brain, you have to generate heat and disorder outside your brain. You're burning calories and energy.
So I can only physically remember the past because the universe allows me to increase its overall entropy to record the data.
Exactly. This is known as the psychological arrow of time. We vividly remember the past and not the future because the universe's entropy gradient only allows our physical brains to record data in that one specific direction.
So I only know who I am, I only have an identity because the entire universe is slowly falling apart.
Essentially, yes. You are riding the long, slow slide of cosmic entropy, and your conscious experience of time is just the wind in your hair as you go down the slide.
That is simultaneously incredibly poetic and deeply bleak.
That's physics and philosophy for you.
Okay, let's move out of the foundations and into the frontier section. Because if space and time weren't weird enough, we have to talk about quantum mechanics.
Ah, yes. The place where human logic basically goes to die.
The outline calls this specific section quantum weirdness and reality. And the central glaring problem at the heart of it all is the measurement problem.
This is the massive elephant in the room of all modern physics. The pure math of quantum mechanics works perfectly. It describes subatomic particles like electrons as wave functions, which are essentially invisible clouds of probability. An electron isn't sitting right here. It's in a fuzzy superposition of being here and there and everywhere in the room all at once.
Right, until we decide to look at it.
Right. The instant we measure it with a detector, the wave function inexplicably collapses. The fuzzy electron snaps instantly into one defined position. The massive philosophical problem is, the math itself doesn't explain how or why that collapse happens. It just describes the wave and then the particle. It's like a proof that just says, and then a miracle occurs.
And the sources show philosophers have been viciously fighting over this exact miracle for 100 years. We have what are called the interpretation wars.
It really is an intellectual war.
Yeah.
And you, the listener, need to understand, these aren't just minor differing opinions on a math equation. These are completely different fundamental realities being proposed, all based on the exact same math.
Let's put the main ones on trial. First up is the Copenhagen interpretation.
This is the orthodox view, pioneered by Niels Bohr. He strongly argued that the wave function isn't real in a physical sense. It's just a mathematical tool we use to predict probabilities in the lab.
So the electron literally isn't a real physical object until I look at it.
Bohr would say asking, where was the physical electron right before I looked, is a fundamentally meaningless question. It's exactly like asking, what is the map of the territory before I even draw the map? It doesn't exist.
That feels like a cop-out to me. It feels like telling a curious student, stop asking hard questions and just do the math.
A lot of modern philosophers completely agree with you. It's heavily anti-realist.
Yeah.
It basically gives up on describing an objective world that exists when we aren't looking at it.
Okay, next defendant in the interpretation wars. Many worlds.
Proposed by Hugh Everett, who was a strict realist. He said, look at the equations. The math clearly says the wave function never ever collapses, so let's just assume it doesn't.
But if it never collapses, why do I only ever see one single outcome in the lab? If the electron could be on the left or the right side of the screen, I only ever see a flash on the left.
Everett says, you absolutely see it on the left. But there's another, equally real you who sees it flash on the right. The entire universe literally branches. Every single time a quantum event happens, which is trillions and trillions of times a millisecond reality splits entirely.
So there are billions of physical versions of me out there.
Infinite versions, arguably. Think about it. In this room right now, we are recording this discussion.
Yeah.
In another branch that split off an hour ago, we decided to get coffee instead and cancel the recording. In another branch entirely, I'm a professional juggler. In another, a cosmic ray hit the primordial soup slightly differently, and life never evolved on Earth at all.
That feels completely excessive. To explain the position of one tiny, invisible electron in a lab, you have to literally invent an infinite number of parallel universes.
It is what philosophers call ontologically expensive. It's a massive philosophical price to pay. But the big upside is that it perfectly preserves the purity of the math. It's entirely deterministic. There's no magical collapse, just endless branching.
Is there a middle ground? Something that keeps our one world real, but doesn't require me to have infinite clones walking around?
There is pilot wave theory, also known as Bohmian mechanics. This one is genuinely fascinating. It says, the particle is completely real, and it always has a definite single position. We just don't know what it is. But it is physically riding an invisible pilot wave, a quantum field that gently guides it exactly where to go.
Like a physical surfer riding an ocean wave.
Yes, perfect analogy. The invisible wave goes through both slits in the famous double slit experiment, creating the interference pattern, but the actual hard particle only surfs through one slit.
That sounds incredibly reasonable compared to the other two. Why isn't every physicist a Bohmian?
Because it requires a massive catch, non-locality.
Spooky action at a distance.
Exactly what Einstein hated. For the invisible pilot wave to work mathematically, it has to instantly know about everything else in the entire system, no matter how far away it is. If I change the setting of a laser detector here on Earth, the pilot wave on Mars has to adjust itself instantaneously, faster than the speed of light. It deeply violates the spirit of relativity, even if it doesn't technically violate the ability to send useful information.
So as a listener, you basically have to pick your poison here. No reality when you aren't looking, which is Copenhagen. Infinite realities constantly splitting, which is many world. Or spooky, faster-than-light reality, which is pilot wave.
Precisely. Those are your options. And if that isn't strange enough, there's the Wigner's friend thought experiment. This completely messed me up when I first encountered it in grad school.
It's an extension of the famous Schrodinger's cat experiment, right?
Right. But it replaces the cat with a human. Imagine a physicist, let's call him Wigner, puts his good friend inside a completely sealed, perfectly isolated laboratory. Inside, the friend measures a single electron. The friend clearly sees the electron flash spin up.
Okay, so for the friend inside the room, the wave function has definitely collapsed. They wrote it down in their notebook.
Right. But Wigner is standing outside the sealed lab. To Wigner, the friend, the notebook, and the entire lab are just one giant, complex quantum system made of atoms. According to the strict math of quantum mechanics, until Wigner opens the door and looks inside, the friend is literally in a superposition of having seen up and having seen down.
But that's absolutely ridiculous. The friend sitting inside knows exactly what they saw. They aren't sitting there in a blurry haze of probability.
That is the core paradox. Can a conscious human observer be in a mathematical superposition from the perspective of another human observer outside the room?
If the answer is yes, then reality is entirely subjective. My physical reality is fundamentally different from your physical reality. We don't share a universe.
And if the answer is no, if the friend inside miraculously collapses the wave function for the whole universe just by looking at the electron, then human consciousness is somehow physically magic. It breaks the linear mathematical laws of quantum mechanics just by existing.
That implies that we, as conscious observers, are somehow actively creating physical reality. Which leads us directly to the biggest, perhaps most profound mystery in our sources: cosmology and fine-tuning.
The Goldilocks universe problem.
I love this topic because it's where hard physics really starts to sound like ancient theology.
It really does. Because when physicists look closely at the fundamental constants of nature, the raw numbers plugged into the equations of the universe, like the exact strength of gravity or the precise mass of an electron, they seem absurdly, suspiciously fine-tuned for biological life to exist.
Give us a concrete example of this tuning.
Take the force of gravity. If gravity were just a tiny microscopic fraction of a percent stronger than it is, stars would burn through their nuclear fuel in a few million years instead of billions. They would die before evolution even had a chance to start. If gravity were just a tiny bit weaker, gas clouds would never clump together to form stars in the first place. The universe would just be a cold, dark, endless cloud of uniform gas forever.
And what about the cosmological constant? That's the underlying energy of empty space itself, right?
Yes. The value of the cosmological constant is tuned to 120 decimal places. That is an unimaginably precise number. If it were slightly larger, the universe would have ripped itself apart so violently fast that atoms could never even form. If it were slightly smaller, the universe would have collapsed back in on itself a fraction of a second after the Big Bang.
So the ultimate question is, why is it so perfect? Why did we hit the cosmic jackpot on every single dial?
Philosophers generally lay out three options. Option one is chance. It's just a brute, lucky fact. We rolled the cosmic dice and got lucky.
That feels incredibly unsatisfying. Winning the lottery once is amazing luck. Winning the lottery 50 times in a row, hitting the exact gravity number, the exact electron mass, the exact expansion rate that crosses the line into highly suspicious.
Most physicists agree it's too unlikely. So option two is design. A literal designer intentionally set the dials to those exact numbers so we could exist. This is the classical theistic argument.
Basically, God did it.
Right. And option three brings back the multiverse again, but used differently than in quantum mechanics. If there are literally infinite universes bubbling up all the time with completely random dials, some have crazy high gravity, some have zero gravity, then the vast majority are totally dead and empty. But purely by statistical inevitability, a tiny fraction will have the exact right numbers for life. We obviously observed this specific perfect one because we couldn't possibly exist in the dead ones to observe them.
That's the anthropic principle. We are here because we are here.
Right. It's a massive cosmic selection bias.
But there was a truly fascinating counter-argument in the sources from the physicist Sean Carroll. He takes this whole fine-tuning problem and completely flips it on its head. He argues that fine-tuning is actually strong evidence for naturalism and evidence against a designer.
This is a brilliant four-dimensional chess move of an argument. I absolutely love this perspective.
How exactly does that work? Because usually religious thinkers point to the incredible complexity of the eye or the tuned universe and say, look at this, it has to be design.
Carroll says, stop and think about the nature of God for a second. If God is truly omnipotent, does he actually need perfectly fine-tuned physics to create life?
Well, no. I mean, he's God. By definition, he could make living, conscious beings out of literal dust or pure light.
Exactly. Or he could create a completely bizarre universe made entirely of milk and honey and just put living souls inside it. An all-powerful God doesn't need a perfectly balanced cosmological constant or specific carbon atoms to make consciousness. life is a direct miracle to a theist. It fundamentally doesn't require physical machinery.
Okay, I see where this is going.
But for a pure naturalist, someone who believes only the physical world exists, life is an incredibly delicate, incredibly complex physical and chemical process. It absolutely requires stable, long-lasting stars. It requires heavy elements like carbon to be cooked inside supernovas over billions of years. Naturalism physically requires a universe that looks exactly like this finely tuned one. So finding a finely tuned, highly specific machine is exactly what a naturalist should expect to find. But it's actually kind of surprising and unnecessary for a theist.
Because if God did it, he could have just done it a million different simpler ways. He wouldn't need to balance an equation to 120 decimal places.
Exactly. The very fact that our lives depend so heavily on such incredibly fragile, specific, physical parameters strongly suggests that those physical parameters are the only thing keeping us alive. There's no magic sustaining us, just the delicate math.
That is a profound inversion of the usual logic. It totally turns the argument from design into an argument of constraint.
So considering all of this, what does this actually mean for us? We've covered the nature of space, the flow of time, quantum branching, and the dials of the cosmos. Section 4 of our outline is implications. Why should you, the listener, driving your car to work right now or doing the dishes, actually care about substantivalism or the block universe?
I think it fundamentally changes how you view your place in the daily world. Let's talk about the laws of nature. We constantly talk about obeying the laws of physics, like they are strict traffic cops enforcing the speed limit of light.
Right, you cannot go faster than light. It's the law, and the universe enforces it.
But there is a philosophical view, in reading the Humean view, that says laws aren't governing rules at all. They are just after-the-fact descriptions of patterns.
This is sometimes called the mosaic idea. Imagine a massive, infinitely complex mosaic of colored tiles. The static pattern of the tiles is just there. It just exists. The laws of physics are just our tiny human brain's attempt to describe the patterns we see in the tiles. The electron doesn't know the mathematical law. It isn't consulting a rule book. It just does what it does. We are the ones who draw the line and call it a rigid law.
So the map is not the territory all over again. Our math is just the map.
Always. But let's get even more existential for a minute. Let's look at the block universe and human free will.
Oh boy, here we go. The heavy stuff.
If eternalism is true, if the future already perfectly exists, permanently etched in that four-dimensional block, then you, the listener, have already finished listening to this exact audio. You have already eaten your dinner tonight. And, to be blunt, you have already died.
So I have absolutely zero real choice in my life. Every decision is an illusion.
It definitely violently challenges our definition of choice. Your choice is just another physical event permanently baked into the block. It's completely fixed. You feel an intense psychological sensation of choosing right now, but the final outcome is already sitting there at coordinate X, Y, Z, and T.
That feels incredibly claustrophobic again. It makes me feel like a puppet just playing out a script I didn't write.
Some modern philosophers trying to rescue our free will with a compromise called the growing block theory.
The growing block. How does that save us?
It says the past is totally real and frozen solid. The present moment is the absolute cutting edge of becoming. And the future is pure, unformed nothingness. We are actively adding fresh layers to the block as we live and make choices.
Okay, that feels better. That gives us our agency back. We are actively building the block of reality.
It does feel much better. But as we discussed earlier, it clashes horribly with Einstein's relativity. If now is completely relative depending on how fast you're moving, how can there possibly be a single, objective, universal edge of the block? You can't have a cutting edge of time if time is relative.
Physics just won't let us have a comfortable philosophy, will it? Then there's the participatory universe idea. This connects right back to the Wigner's friend quantum paradox.
Yes, John Wheeler, an absolute giant of theoretical physics, proposed this. He drew a very famous, simple diagram of the entire universe as a big letter U shape. At the top of one end of the U is the Big Bang, the beginning of time. At the top of the other end is a giant eye representing human consciousness looking back across the void at its own beginning.
The universe literally observing itself.
He strongly suggested that the universe might logically require conscious observers to actually come into concrete being, that dead matter alone isn't enough to make a reality. You need mental information and observation to crystallize the fuzzy quantum probabilities into a hard reality. He coined the phrase "it from bit." Every physical particle, every it, ultimately derives its existence and function from bits of information elicited by our yes or no quantum measurements.
That sounds almost totally mystical.
It closely connects to a modern philosophical concept called inclusive materialism. It's the radical idea that matter isn't just dead, dumb stuff bouncing around, that human consciousness and biological life are actually fundamental, necessary parts of the material story of the cosmos, not just weird accidental byproducts on a wet rock. We aren't just cosmic mold. We are the literal mechanism by which the universe is able to know it exists.
Which brings us perfectly to the final major point of this whole discussion, the absolute necessity of philosophy.
Yes, because there is a very strong, very vocal tendency in modern pop science to proudly declare that philosophy is dead. Stephen Hawking famously wrote it on the first page of a book. Neil deGrasse Tyson has said very similar things in interviews. The attitude is basically, philosophy is useless wordplay, just shut up and do the experiment.
Shut up and calculate. That's the famous physicist mantra.
Exactly. But as we've hopefully seen today, you literally can't just calculate your way out of these problems. When a theoretical physicist talks passionately about the multiverse, they are talking about something fundamentally unobservable by definition. You can't ever run an experiment on a universe outside our own. You have to rely entirely on pure logic, probability theory, and conceptual analysis. That is doing philosophy.
And when you fiercely debate the interpretation of quantum mechanics, that is pure philosophy. The math on the chalkboard is exactly the same for Niels Bohr as it is for Hugh Everett. The story we tell ourselves about what the math means is philosophy.
Exactly right. Philosophy is what keeps physics honest. Physicists throw around heavy words like law, cause, observer, and reality all the time. Philosophers act as the rigorous lawyers of the scientific world. They step in and ask, wait, carefully define your terms. Is that logical leap actually sound? Without that strict philosophical rigor, hard science risks decaying into scientism, a blind dogma that insists only physical measurement counts for anything, even when you're explicitly studying the unmeasurable boundaries of existence.
So, coming to the end of all this, we aren't just biological machines passively riding a wave of entropy inside a frozen four-dimensional block.
Well, we might be. The physics allows for it.
Yeah.
But we are biological machines that uniquely possess the capacity to mathematically and philosophically understand that we are riding that entropy wave and that profound self-reflection. That's where the real magic of existence lies.
Here's where it gets really interesting for me, leaving the listener with a final thought. If that third way of space-time is fundamentally true, if base reality is just a pure structure of relations and not isolated things, then we humans aren't isolated individuals either. We are literally defined down to our subatomic core by our connections to absolutely everything else in the cosmos.
A truly beautiful thought to end on. We are the web. We are the structure.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.